Swayam Prabha. Digital India. Educated India.
In this week, we started moments and inequalities. Already we discussed in the last lecture mean and variance. Mean is nothing but the first order moment and the variance is nothing but the second order moment of the random variable. In the last class, we have discussed the first order moment and the second order moment with the examples. In this lecture, we are going to discuss higher order moments. Since we have already discussed first and second order moment, now we are going to discuss any nth order moment for the random variable if it exists. Followed by, we are going to discuss the moments inequalities. So, let me start with the definition of higher order moments. Higher order moments. The definition, that is nth order moment about the mean. Let x be a random variable with nth order moment about the mean value exist. Then one can define with the notation mu suffix n, that is nothing but expectation of x minus, the expectation of x is denoted by mu, that is mean, x minus mu power n, that is going to be the nth order moment about the mean. Whenever it exists, we can denote it by mu suffix n. Whenever it exists, that is the right hand side expectation exists, then you can denote by the letter mu suffix n, that is expectation of x minus mu power n, where n can take the value, it could be 1, 2 and so on. Obviously, if you take the value n is equal to 1, that is nothing but the mu suffix 1 is expectation of x minus mu, that is same as expectation of x minus mu, that is going to be 0. When n is equal to 2, then it is nothing but the variance of the random variable x. So, provided the right hand side expectation exists, then one can define the nth order moment about the mean with the notation mu suffix n. The same way, I can define the nth order moment about the origin. Nth order moment about the origin, or some books they use the word 0, both are one and the same. Let x be a random variable with nth order moment about the origin value exists, then one can define with the notation mu suffix n dash, that is nothing but expectation of x power n. Here again n can take the value 1, 2 and so on. So, when n is equal to 1, this is nothing but the mean or expectation of the random variable, and 2 onwards it is going to be called as a nth order moment about the origin, provided the expectation exists. That is very important. One can relate the second order moment about the origin with the second order moment about the mean. For example, mu suffix 2 dash, that is expectation of x square and mu suffix 2, that is nothing but the expectation of x minus mu the whole square. This is same as variance of x. So, the expectation of x minus mu whole square, if you expand, that is expectation of x square minus 2x mu plus mu square. Expectation is a linear operator. So, it is expectation of x square minus 2 and mu are constant. So, it is expectation of x, and mu is a constant. So, mu square constant, expectation of mu square, that is mu square. So, when you simplify, you will get expectation of x square minus this is 2 mu into mu, therefore 2 mu square plus mu square. So, that is same as expectation of x square minus mu square, that is same as mu 2 dash minus mu 1 dash. That means mu 2 is nothing but mu 2 dash minus mu 1 dash the whole square. So, that means one can write central moment about the mean in terms of central moment about the origin. Next, I am going to give the one important result as a theorem. What the theorem says, if x is a random variable such that mu suffix n dash exists, then mu suffix or dash exists for all or less than n. That is a theorem. Whenever for a random variable, if the nth order moment about origin exists, then all the nth order moment about the origin exists for all or less than n. You can give the proof of this theorem. Given mod of x power r which is lesser than 1 plus mod x power n, this is for all x belonging to real, we can conclude, suppose you consider x as a continuous type random variable, minus infinity to infinity mod x power r f of x dx, where f of x is the probability density function of a continuous type random variable, that is less than or equal to minus infinity to infinity 1 plus mod x power n times f of x dx. That is same as 1 plus minus infinity to infinity mod of x power n f of x dx. And since the nth order moment about the origin exists, therefore this quantity is going to be finite, the integration quantity, therefore this whole quantity is going to be finite. This implies minus infinity to infinity absolute of x power x f of x dx is a finite, that is for all r which is lesser than n. So this is given. We can include one more statement for r less than n, given for r less than n mod x power r which is lesser than 1 plus mod x power n. This is true. Therefore, both side you can do the integration by multiplying f of x, and given that it is an nth order moment about the origin exists, therefore for all r less than n the moment of r exists also. The next result as a theorem, let x be a random variable whose rth order moments exist, then one can write mu suffix n is same as summation over k is equal to 0 to n ck mu suffix k dash with minus mu 1 dash power n minus k. This can be proved whenever nth order moment exists, then one can write the nth order moment about the mean is same as a function of all the previous order moments about the origin. The proof is as follows. You start with mu suffix n, that is nothing but nth order moment about the mean, that is x minus mu power n. That is same as the expectation of x minus, one can write mu as the mu 1 dash, that power n. Now you can go for the binomial expansion of x minus mu 1 dash power n. That is same as expectation of summation k is equal to 0 to n ck x power k and minus mu 1 dash power n minus k. that is same as the nck is a constant, that's not random, minus mu 1 dash, that is also not random. Therefore, expectation can be taken inside, that is summation k is equal to 0 to n nck expectation of x power k minus mu 1 dash power n minus k. I can rewrite expectation x power k as the kth order moment about origin. Therefore, this is going to be summation k is equal to 0 to n nck mu suffix k dash multiplied by minus mu suffix 1 dash power n minus k. Because of the previous theorem, when the nth order moment about mean exists, that means all the previous order also exist. Therefore, this is a valid statement. With the help of previous moments about the mean, you can always find the moment of nth order about the origin. In conclusion, with the previous starting from first to nth order moment about the origin, one can get nth order moment about the mean. One can go for one easy example of how to find the nth order moment for some random variable which is of the continuous type. Let x be a continuous type random variable with probability density function f of x is 1 divided by sigma times root pi e power minus x minus mu divided by sigma the whole square multiplied by 1 by 2, where x lies between minus infinity to infinity. So, this is a probability density function of a continuous type. Later we are going to call it as the normal distribution when we are discussing standard distributions. So, now we will keep it as a continuous type random variable with the probability density function 1 divided by sigma times square root of 2 pi e power minus 1 by 2 x minus mu by sigma the whole square. Always the sigma and mu values are given. One can say the mu value can lies between minus infinity to infinity, whereas the sigma quantity is always greater than 0. What is the meaning of mu and sigma? That also can be discussed. In this example, if you find out expectation of x, that is minus infinity to infinity x times probability density function, with the assumption that the expectation exists, we will try to find the value minus infinity to infinity x times f of x dx. This is going to be, after simplification, you can get the answer, that is mu. I am not going for the simplification of this integration as it is. If you substitute the f of x, x times f of x integration minus infinity to infinity, you can get the value mu. This mu is going to be called it as a mean. That is called the mean of the random variable x here. Similarly, if you compute expectation x square, nothing but minus infinity to infinity x square times f of x dx, one can able to get by after some simplification, you can get mu square plus sigma square. Substituting f of x is 1 divided by sigma times the square root of 2 pi e power minus 1 by 2 x minus mu by sigma whole square. Therefore, the variance of the random variable x, that is expectation of x minus the mean is mu the whole square, that is same as expectation of x square minus expectation of x the whole square. Just now we got it, e of x square is mu square plus sigma square, and expectation of x, that is mean, that we got it as a mu, that is a minus mu square. Therefore, you get variance is sigma square. That means for this continuous type random variable, the mean is going to be mu and the variance is going to be sigma square. We have another measure, that is a positive square root of variance, that is called the standard deviation. So here the sigma is the standard deviation, because sigma square is a variance, and the positive square root of variance, that is called the standard deviation. For this continuous type random variable, the sigma is the standard deviation and sigma square is the variance. So we got first moment, that is the mean, variance we got it as sigma square. Now we can go for higher order moments, that is expectation of x minus mu power n for n is equal to 3 onwards, because for n is equal to 2, that is same as variance, we got it already. So we are computing the nth order moment about the mean from 3 onwards, that is same as minus infinity to infinity x minus mu, mu is a mean, power n 1 divided by sigma square root of 2 pi e power minus 1 by 2 x minus mu by sigma the whole square dx. If you see the integration very carefully, when n is a odd positive integer, then the integration value is going to be 0, because e power minus 1 by 2 x minus mu divided by sigma whole square is a positive, is a even function. When n is a odd positive integer, the whole integration values is going to be 0. Therefore, you can immediately conclude this is going to be 0 for n is equal to 3, 5 and so on. Now the question is, what is the value when n is going to be the even positive integer? By even positive integer, one can simplify this integration and you can get the answer, that is n minus 1, n minus 3 and so on till multiplication of 3 into 1 times sigma power n, when n is going to be 2, 4, 6 and so on. So for this continuous type random variable, which is nothing but the normal distribution with the mean mu and the variance sigma square, we are finding the nth order moment about the mean for all. For all the odd powers, it is going to be 0. For the even, you get the expression is n minus 1 into n minus 3 and so on, 3 into 2 times sigma power n when n takes the positive, even positive integers.